Hi, my name is Sue. In this lesson, we'll look at exponential functions and their graphs, logarithmic functions and their graphs, and applications of these functions. An exponential function with a base b, where b is greater than 0 and b cannot be 1, is a function f of the following form. F of x equals b to the x, where x is any real number. Think about why the function's base is restricted to being positive and it cannot even be 1. Well, starting with the value 1, 1 to any power is always the value 1, and so would not have the same properties as the exponentials would. We have the same issue with the value 0 being used as the base. The base cannot be negative in case we want to take even roots of the base, like the power of a half or a fourth. So leaving these values out, we'll keep our exponential functions having consistent properties. Example 1. Graph f of x equals 3 to the x. If we start by thinking about our domain, then we realize that 3 can be taken to any power. So we need to plot 0, some positive values, and some negative values for x. We'll start by looking at x is 0. And then we'll go to the right. And then we'll graph values to the left. So if x is 0, 3 to the 0 is 1. If x is 1, 3 to the first is 3. If x is 2, 3 squared is 9. And we see that we have a pattern as f of x is getting larger and larger. If we have negative values, then 3 to the negative 1 is the same as 1 over 3. And 3 to the negative 2 then would be 1 over 3 to the positive 2, or 1/9. And 3 to the negative third, which would be 1/27. So we can see these values are getting closer and closer and closer to 0. Let's see how those look on a graph. At 0, we go up 1. At 1, we go up 3. And at 2, we go up 9. So as we go to the right, we can see that our graph will rise quickly or exponentially. But as we go to the left, we have negative 1 up a third, negative 2 up a ninth. We see that it's falling very slowly. It's going to get closer and closer and closer to this red dotted line. However, there's no power of 3 that will ever yield 0, so we'll never reach 0. To show this on our graph, we need to draw a dotted line along the horizontal asymptote, showing that y will never be 0. This is a boundary line for our graph. Now let's take a look at what happens when the base of our exponential is between 0 and 1, say a third. We'll approach this graph of the exponential in the same way that we did the last example, starting first at 0, which gives us the same value because any number to the 0 power, except 0, is 1. So this point will be on every graph. And then 1 would give us 1/3 to the first is a third. 1/3 squared is a 9. So instead of getting larger and larger, these values are approaching 0. And then as we let x be negative, 1/3 to the negative 1 will become its reciprocal, so it will become positive 3. If I take it to the negative 2, it will become the reciprocal squared, or 9. And negative 3 would become 27. So you see these are rising exponentially. So looking at this graph, we have at 0 we go up 1, at 1 we go up a third, at 2 we go up a ninth. So these points will take us closer and closer and closer to our horizontal asymptote. But again, there is no value of a third to some x value that will ever give me 0 as a y value. So I'll never reach this horizontal asymptote. As we move to the left, then we have negative 1 goes up 3, negative 2 goes up 9, and it goes up quickly to the left. But since we read our graphs left to right, we can say it falls quickly and approaches 0. Looking at both graphs, we see some of the main characteristics of the graphs of exponential functions. So characteristics of the graph of f of x equals b to the x. The graph will always contain the point 0, 1, because b to the 0 equals 1. And when b, our base, is greater than 1, then the graph will rise from left to right, as we saw in our first example. When b is between 0 and 1, then the graph will fall from left to right. The x-axis will be the horizontal asymptote. The domain is all real numbers, or negative infinity to positive infinity, while the range is 0 to infinity. A well-known formula that uses exponentials is the compound interest formula. As opposed to simple interest, you earn interest on both the principal and the interest, each compounding period n. So suppose that a principal of $P is invested at an annual interest rate R in percent, but expressed as a decimal, compounded n times per year. Then the amount A, accumulated after T years, is given by the following formula. A equals P times the quantity 1 plus R over N to the NT. If we compound the interest every moment in time, which means there isn't a moment when the interest is not being compounded, then we call this continuous compounding. Suppose that a principal of $P is invested at an annual interest rate of R in percent expressed as a decimal, compounded continuously. Then the amount A, accumulated after T years, is given by the following formula. A equals P e to the RT. Remember, e was the natural number. It has an approximate value of about 2.72, and you'll see that it shows up quite a bit in math. Example 3. Suppose you invest $10,000 at 5.5% annual interest, compounded monthly. How much money would you have after 5 years? Part A, we're compounding monthly. We'll use the first formula, which tells us that A equals P times the quantity 1 plus R over N to the NT. So since we're looking for how much money we would have, then we want to solve for A. P is the principal, or the amount invested. We invested $10,000 in this case. 1 plus R is the interest rate. Since it's 5.5%, we need to change that to a decimal, 0.055. N is the number of times per year that it's been compounded. And since it's monthly, then N would be 12. And then we need to take it to the power N times T, or N, again, is 12, and T is the number of years, so we have 5 years. So typing all of this in our calculator, we would get a final amount of $13,157.04. Now in the second problem, we're compounding continuously. So now we'll use the formula A equals PE to the RT. So A is P is still 10,000. E is a constant, it's not a variable. R is still 0.055%. And T is still 5 years. So typing this in our calculator, you'll see that we'll have just slightly more than if we compounded monthly. So we have $13,165.31. Next, we'll look at the inverse of exponentials, called logarithms. The definition of the log base b of x is for b is greater than 0 and b cannot be 1, then if b to the y equals x, then y equals the log base b of x. Comparing the idea that numbers can be written in more than one way, like a half is written as a fraction, but it can also be written as a decimal, as 0.5, or percent as 50%, then exponentials can be written in another way, as logarithms. So looking at one example, if we have 2 cubed equals 8, this is a statement in exponential form. If we change it to logarithmic form, then we see that the exponent is the number that comes out, So we'll have 3 equals the log base. The base of the exponential and the base of the log are the same, so log base 2 of 8. Now, looking at this more closely, we can see that logarithms are the inverse of exponentials, because rather than reading logs as log base 2 of 8, we can ask ourselves the inverse question, or in other words, 2 to what power would give me 8? And that's why I have an answer of 3. Now let's take a look at the graphs of logarithmic functions. To graph a logarithm, it's often easiest to change forms to exponential form before finding ordered pairs to graph. So we'll let this be y, and then changing forms, we have 2 to the y equals x. So in this case, we'll be plugging in values for y to see the matching x values. So I'll use x and y here. Now starting with y is 0, we get 2 to the 0 is 1. And then if we let y be 1, 2 to the first is 2. Then let y be 2, we get 2 squared is 4. If we let y be negative values, then you see that 2 to the negative 1 gives me a half. 2 to the negative 2 gives me a fourth, and 2 to the negative 3 gives me an eighth. So taking a look at those ordered pairs, we have, going to the right, we have 1, 0, 2, 1, and 4, 2. So as I go to the right, my graph is increasing, but slowly rather than exponentially. It increases slowly. And then, as I get closer to 0, you'll see that at a half, I have negative 1. At an eighth, I have negative 2. So instead of having an horizontal asymptote, we now have a vertical asymptote. So this graph will approach this vertical line, but will never reach it. This tells us that the domain of a logarithm is only positive real numbers. Here are some of the main characteristics of the graphs of logarithms. The graph will always contain the point 1, 0, because the log base b of 1 equals 0. Or if we look at this in exponential form, we'll see that b to the 0 will always equal 1, as long as b is not 0. So when b is greater than 1, the graph will rise from the left to the right, or from the fourth quadrant to the first. And when b is between 0 and 1, then the graph will fall from left to right, from the first quadrant to the fourth. The y-axis is now a vertical asymptote, and the domain and range have been swapped from our exponential functions, so the domain is all positive numbers, or 0 to infinity, and the range is from negative infinity to positive infinity. In this lesson, we looked at exponential functions and their graphs, logarithmic functions and their graphs, and applications of these functions. Now it's time to go into the homework section and work some problems on your own.